Good morning. Welcome to today's webinar. It's titled Fitting Classification and Regression Trees Using Statgraphics in R. My name is Neil Paulimus. I'm Director of Development for Statgraphics, and it pleases me to be able to show you how to build different types of decision trees. Now, classification and regression trees are machine learning methods that are used to construct predictive models from data. When building a tree, we recursively partition the data space using simple binary decisions. The results are commonly portrayed as a tree with a split at each decision node. If you haven't seen a decision tree before, here's a typical example. It's based on Fisher's iris data. His data consists of 150 samples of iris. They're divided into three species: Setosa, Versicolor, and Virginica. Each iris has been measured in four ways. The length of the petal and the width of the petal have been measured, and also the length and width of the sepal. Based upon the 150 observations in what we'll call the training data set for this particular model, a tree's been built. The way you read the tree is the following. Let's suppose we take an iris, perhaps one of unknown species. We begin at the top of the tree and first measure the length of the petal. If it's less than 2.45, we move left. If it's greater or equal to 2.45, we move right. So if it's less than 2.45, we'll move to the left, come down to this terminating node, also called a leaf, and classify that iris as Setosa. Now you can also see the probability associated with that classification. Amongst the 150 iris in the training data set, the only samples that made it to this particular location are Setosa, so we estimate the probability of being Setosa if you end up at this terminating leaf to be 1. If the petal is 2.45 or greater, we move to the right and then look at the width of the petal. If the width is less than 1.75, we move left. If it's greater or equal to 1.75, we move right. Then we might look at the length of the petal again, the length of the sepal, and so forth. And eventually, based upon the binary decisions at each of these nodes, we'll end up at one of the 1, 2, 3, 4, 5, 6 terminating leaves. Now you may notice that in some cases, if you travel down a branch, for example, way to the right of the tree, on the last split based upon the petal length, whether you go left or right, it classifies you as being Virginica. However, if you go to the right, we're quite certain of that. The only samples that made it to that leaf were Virginica. Most of the samples that made it to this leaf were also Virginica, but not all of them. So you see the probabilities differentiating sometimes one leaf from another. Let's take a look now at the basic structure of the model underlying the decision tree. There is a single variable y that's the variable to be predicted. If that variable is categorical, then we'll construct a classification tree. If the variable is continuous, we'll construct a regression tree. There are also p predictor variables x, each of which may be either categorical or continuous. To build the decision tree, we'll use the partitioning algorithm. We start at the root node. That's the node at the very top of the tree. We then check all of the predictor variables x sub j and find the split that minimizes the resulting average within node deviance. I'll talk a little bit more about that in just a couple minutes. If the x we select is a continuous variable, then the split will be of the form x sub j less than some constant c. If that's true, you go left. If it's false, you go right. If the x variable we select happens to be a discrete variable, then the split divides the possible values of x into two distinct groups. Now, if one or more stopping criteria are met after we make a split, we stop. Otherwise, we look at the child nodes we created and consider splitting them. The first data set we're going to look at is a data set I've looked at in previous webinars. It's information about the passengers on board the Titanic the night she sank. There were a total of 1,309 passengers. And we have a data file in which we have a single row for each of the passengers. The first column is called survived, and that tells us whether or not that individual in that particular row survived. We also have columns showing what class ticket an individual purchased, first, second, or third, their sex, their age, how many siblings they had on board, how many parents or children they had on board, how much they paid for their ticket, and finally, which of three locations they embarked at. I'm going to now go to Statgraphics, load up that data, and build what will be a classification tree, because what we're going to try to predict is whether an individual survived. I've loaded the data for the Titanic into the Statgraphics data sheet. To fit a decision tree, I'll go to our interface, Classification and Regression Trees. Survived is going to be the dependent variable. We have categorical factors, the class ticket, sex, the number of siblings, the number of parents and children, and where they embarked. I'm going to choose age and fare as my quantitative variables. On the Analysis Options dialog box, the first thing I need to do is be sure that I pick the right type of tree. Since survived has only two values, yes or no, we'll be building, in this case, a classification tree. I also want to be careful and select certain options regarding partitioning. This controls how complicated a tree I'll get. The first thing I specify is the smallest allowed node size to be partitioned. I'm telling it do not partition any nodes that have less than 10 observations at them. I can also specify the minimum number of observations in each child. And here I have it set to 5. That means that when I split a node, each of the children must have at least 5 observations. I can also specify the minimum within node deviance in order to do a split. Now, we need to go back to my slides and talk for just a minute about node impurity. Node impurity measures how much variability there is among observations that make it to a particular node. We measure impurity in a tree using something called the residual mean deviance. For example, take a look at my notation. Let's let n be the number of observations in the training set. Those are the observations in my data file that are used to build the tree. I'll let k be the number of leaves. I'll let p sub ij be the proportion of data of the same type as I that are assigned to leaf j. I in this case would be survived or not survived. In the case of a regression tree, y hat sub I would be the predicted value of observation I. We measure the residual mean deviance of a classification tree by summing across all the observations minus 2 times the log of the proportion of the data of type I that have been assigned to leaf j. Add across all the observations and divide by n minus k. We'll get the smallest residual mean deviance if the p for one class at a leaf is 1 and for the other class or other classes 0. So it's a measure of just how much variability there is amongst the classes of observations that make it to a particular node. In the case of a regression tree, the residual mean deviance is just the sum of the observed minus the predicted value squared divided by n minus k, which is a typical mean squared error. Some of the other options we have on the Statgraphics Analysis Options dialog box have to do with pruning the tree, which I'll talk about in a few minutes, which observations I want to use in the training set, and in this case I'm going to use all rows, although sometimes, as you'll see, I might like to leave certain rows out of the fit and use those to validate the tree that was trained by the rest of the observations. We also have a few options that control how the R tree plot looks. I'll go ahead and just take the defaults by pressing OK. And now there are several things I'd like to look at. I'm going to ask to look at the analysis summary, the R tree diagram. We're going to want to look at the R tree structure, the node probabilities, and the classification table. I'm also going to want to look at the tree diagram and the deviance plot. When I press OK, it will actually put together a script, send the script to R. R will read the data, fit the tree, send the results back to Statgraphics, which is captured and placed in this analysis window. The first bit of the output I want to look at is the decision tree. And here I'm going to increase the size of the font so I can see it a little bit better. You start at the root node, and the first variable it's selected to build the classification tree was sex. Sex was the single variable that reduced the residual mean deviance the most. Okay, if you're female, you go left. If you're male, you go right. Of all the females, the next most important thing to look at was the class of ticket. If you had a third class ticket, you'll go left. If you had a first or second class ticket, you go right. Now, if you're female and you had a first or second class ticket, the prediction is yes, you would have survived. On the other hand, if you had a third class ticket, it mattered what fare you paid. And for whatever reason, if you had a relatively low fare, we'll predict you survive. If you paid more for your ticket, we'd predict you didn't survive. As far as males are concerned, the most important factor determining survival was age. If you were less than 9.5 years, a relatively young boy, you'd go to the left. If you had 3, 4, or 5 siblings, we predict you did not survive. If you had something other than that, we'd predict you did survive. For the older boys, it mattered a little bit what type of ticket you had. Was it a second or third class ticket, in which case you'd go left? If you had a first class ticket, you'd go right. Now, unfortunately, no matter what class ticket you have, we'll predict you don't survive. But if I go to pane options and I ask for a couple decimal places for probabilities, it'll tell me what the probability of that particular classification is. And here you can see there's a little bit of a distinction. If you were a male over 9.5 years old with a second and third class ticket, there was about an 87% chance you did not survive. On the other hand, if you were a male of the same age and had a first class ticket, the probability of not surviving was a little less. It was about 66%. I can see more details about the tree if I double-click to put the graph away and then click on the pane labeled R Tree Structure. Here you see each node of the tree identified. Nodes consist of the decision nodes where a branch occurs and also terminating nodes, which are the leaves. You can see, for example, the first node, the first decision node, had to do with sex. It splits left for females and right for males. The second node had to do with the class ticket. It split left if you had a third class ticket, right if you had a first or second class ticket. It also shows you how many passengers arrived at each of the nodes, what the deviance was, the calculated deviance, and what the majority of the people that arrived at a particular node, what class they were. Did they survive or did they not survive? So you can look at this and get a lot of detail about how that tree was constructed. It's also useful to look at the table of node probabilities. This tells us of all the observations that arrive at a particular node, what is the probability of a no, what's the probability of a yes. For example, if you look down here, nodes 12 and 13 were at the bottom right of my tree. We had 466 passengers who arrived at node 12. They all had third class tickets. Those were the older boys and men with third class tickets. 87% did not survive, about 13% did. Of those with first class tickets, 66% did not survive, about 33-34% did. We can also look at a table, the classification table. This will take all the observations in the training set. And you can see there are 1,309 passengers in that particular training set. Of those passengers, 809 did not survive. Our tree would have correctly predicted that 709 of them would not survive. It would have gotten some of them wrong, though. 100 passengers would have been predicted to have survived who did not. So we have about an 87% correct classification for those people that did not survive. For the 500 people that did survive, we correctly predicted about 71.6%. Overall, the tree predicts correctly 81.5% of the 1,309 passengers on the Titanic. In building the tree, you'll notice that I used all of the passengers to decide what variables and what splits to use in the tree. I could, if I wanted to, go to analysis options and withhold some of those observations. For example, I might decide to use only the first half of the rows to fit the tree and use the rest of the rows to validate the results. Or I could tell it use the first 500 or whatever. What I think is often a good method is to actually tell it to use every other row. Take every other row, use that to fit the model, and then use the other rows to validate it. Now what happens if you pick a training set and press OK? R will give you two tables. It will show you, in this case, the results for the 655 observations used to fit the tree, of which about 81% were predicted correctly, and the 654 rows that were not used to fit the tree, of which about 79% were predicted properly. Now we'll often see a little degradation in the percent of training cases correctly classified if we move from the training set to the validation set. This is actually pretty good. We only lost about 2%, meaning at least giving us some feeling that we probably have not overfit the data. One sign that you've overfit your model is when the results for the validation set are much worse than for the training set that was used to actually fit the model. Just as in other types of statistical modeling, when you're building a decision tree, it's important to maintain a balance between getting a tree that's complicated enough to make good use of your predictive variables, but not so overly complicated that it predicts your data well, but is not any good for predicting additional observations. When we build trees, there are two ways we can control the complexity of the tree. One is from the top down, as we did before, by specifying certain options for partitioning. For example, telling the program, don't give me a tree where there are any less than 5 observations in a particular leaf. The second is by doing what's called pruning. When you do pruning, you start with a very complicated tree, and then you start removing leaves and branches until you get down to a tree of the proper complexity. Now in Statgraphics, we have two ways that we can do pruning. One is by specifying the number of leaves. The second is by doing something called cross-validation. What I'm going to do now for you is a cross-validation experiment. Actually, a 10-fold cross-validation experiment. What this means is that I'm going to take my training set and I'm going to build 10 trees. Each time I build a tree, I'll leave out 10% of the data and then average the results. Leave out 10% of the data, build a tree, see how well that tree fits the 10% of the data I did not include, and average those 10 runs of that particular experiment. Basically, this allows me to use all the observations for both training and validation. Now, you do it by making some entries on the Analysis Options dialog box. First, you reduce the within node deviance. You can see here I've gone in and reduced the minimum within node deviance to allow for a split to 0.001. What that's going to do is cause it to fit a quite complicated tree. And then I'm going to ask it to do a cross-validation to reduce the complexity of the tree. So let's give it a try. I'm going to go to the Analysis Options dialog box. First thing I'll do is I'll set Training Set again to all rows. I'll then go and reduce the minimum within node deviance to 0.001. I'll ask it to start by fitting a very complicated tree. And let's take a look at the tree. There's the tree that it decided to fit. Very, very complicated tree, definitely overfitting the data. The next thing I'll do is I'll go back to Analysis Options and set Pruning to Cross-Validation. Down here where it says Number of Leaves, I'll tell it the most complicated tree I want to fit. And it'll run that tenfold cross-validation experiment and find the best tree with 10 leaves. So let's go ahead and press OK. And R has now selected a tree with 10 leaves. Now, why 10 leaves? Well, that was the most complicated tree I wanted it to fit. Not necessarily the best tree, but there is a way that I can probably figure out what the best number of leaves is. If I go and look at something called the deviance plot, you can see what the residual mean deviance was for a tree with one leaf. That's basically everybody in one node, nobody split. When I split it into 2 leaves, the deviance went down quite a bit. It went down when I split it into 3 leaves. Didn't go down when I split it into 4 or 5 leaves, but finally did go down when I split it into 6 leaves. 7, 8, 9, 10, no change in the deviance. So it really looks like a tree with 6 leaves is going to be a good tree. I'll go back then to Analysis Options, tell it I want a tree with 6 leaves, and we'll go ahead and look at the tree, and there it is. Basically, we're splitting first on sex, then, as we've seen before, the class of the ticket for the females. And actually, the females class is the only thing that's important in this particular tree. If you're female and you had a third class ticket, 53% chance you would not survive. If you were female and had a first or second class ticket, 93% chance you did survive. On the other hand, if we look at males, there is a split on age. And for the youngsters, the next split is on the number of siblings they had. And for the older males, it was the class of the ticket that mattered. Now, once you have fit a tree, it's often desirable to use that same tree to predict additional unknown observations. Now, obviously, there are no more passengers that could ever ride the Titanic, but often when you're building these trees and so forth, you're doing it based upon a known training set so that you can go ahead and predict unknown observations. Now, the way you do that in Statgraphics is you go back to the data sheet and you go down to the bottom of the data sheet. Remember, I said there were 1,309 observations. Let me keep on going down. I'm almost down there. And I'm going to add some additional rows. In this case, I believe it was 2 rows I added to the file. Yeah, there they are. Rows 1310 and 1311. I'm going to leave the classification, the dependent variable, blank, but I'll fill in information on all the other variables. So just for fun, I decided to make up 2 imaginary passengers. They both have first-class tickets. One's a female, one's a male. They're both 35 years old, and they have 2 children on board. Okay, now, to see what would happen, what at least the model predicts would happen for those additional rows, I'll go to my list of tables and graphs and ask for predictions and residuals. And here, it will make predictions for all the members of the training set and also for those additional observations. So you see here for the 2 people, the female, it predicts yes, you will survive. For the male, it predicts no, you won't. It also shows what leaf they end up at. The female ends up at leaf 4. The male ends up at a leaf 11. And then if you want, you can go back to the node probabilities, and you can see at node 4, that's for the female, the probability of survival was about 93%. For node 11, for the male, the probability of survival was only about 34%. All right. In the last few minutes we have here today, I want to look at a second example. The second example uses data from the World Bank, data about most countries in the world. And what I'm going to do with this particular data, and I've looked at it in previous webinars, I'm going to build a decision tree to predict life expectancy. Now, life expectancy is a quantitative variable, so what I'll be building in this case will be a regression tree instead of a classification tree. The tree I'm going to build will use 1, 2, 3, 4, 5, 6 columns to be quantitative predictors. For example, I'm going to tell it I want to predict life expectancy as a function of population density, the age dependency ratio, the percent of females in the country, the per capita GDP, the percent of the population that looks in rural areas, and the fertility rate. Now, I won't go through the whole analysis for you, but I will show you what the result is so you can see what the difference is between classification trees and regression trees. Here's the final decision tree that I built. It's predicting the life expectancy. It's a standard tree similar to what we saw for the Titanic data. At each decision node, it looks at a particular variable. The first one it picked was actually the fertility rate. That's the average number of children that a woman has in that particular country. If they have less than 3.3 children on average, you move left. More than 3.3, you move right. Other variables that turned out to be important: GDP per capita, percentage of females, the population density, the age dependency ratio. The important thing to see, though, is as you move down the tree, Let's say, for example, the fertility rate was less than 3.3 children and the per capita GDP was greater than $11,068. I predict a life expectancy, an average life expectancy in that country of about 79.5 years. See, rather than a yes or a no, you're making a quantitative prediction of, in this case, the life expectancy. And what it is, incidentally, what the prediction is, it's the average of all the observations in the training set that make it down to that particular leaf. So of all the countries with low fertility rate and high GDP in that particular data set, the average life expectancy was about 79.5 years. Now you can see that that contrasts quite dramatically with some other leaves. You see leaves over here with life expectancies, predicted life expectancies of 50.5, 55.5. And those are countries with high, actually very high fertility rates. So that's a regression tree. As always, I'll be posting this recording, a recording of this webinar, together with the Statfolios and data files at www.statgraphics.com/webinars. The package that we've used here to fit the trees is a freely available package in R. It's called Tree, developed a few years ago. Those of you who are interested in more details about how classification and regression trees are constructed should take a look at this classic text by Leo Bryman and some other folks. Again, thank you for attending the webinar. I'll be taking questions in a little while.